Okay, so just so that you can differentiate between the two things. We just in 7.2, we learned a confidence interval around a proportion or a percentage. A proportion is the same really as a percentage, right? As that M&N problem in our sample, there was 8%, but they claim the population is 13%. And we said p hat is 8. I already gave out the 7.3 papers, didn't I? Some time ago. And these are going to be your questions for today we're going to work on. Okay. So again, that's proportion, that's percent. How many Democrats have a tattoo? That was problem number 31. They say it's 15%. Okay? Percent, proportion. When we go into 7.3, the difference is now we are going to make an estimate of the mean, the population mean. So we're going to be taking sample mean, and we're going to be making an inference about the value of the corresponding population mean. Before we took the sample proportion and made a interval of whatever confidence, and that was the proportion of the population. Remember p hat and p. Now we're really doing the same thing, but it's about the mean. The mean of the population is what we're estimating from the sample mean. So just like we did with proportion, the sample mean x bar is the best point estimate, 1 point estimate of our population mean. Well, because it's only a sample, we can't say that it's directly that, right? So we're going to then make an interval, just like we did with proportions, at a specific confidence level so that we can estimate that population mean. Okay? And just like we did with proportions, the last part of that section was we found out how to calculate a sample size needed. And we're going to calculate how to do a sample size needed to determine an estimate for the population mean. So that's the difference between the two sections. There's going to be some different formulas that we're going to use, and often we will not know sigma. And think about that. That makes sense because sigma is what? Our population standard deviation. Well, the population standard deviation, if I knew the population standard deviation, would I even need to make an estimate of the mean? No, I would have it, right? So most oftentimes I don't have that. Well, there's where it comes into the student t-test, which is this table that I just distributed on this pink laminated paper. Do we have an extra? I need to get more printed. If you're sitting close to someone, if you'll just share. I may not have enough. There's 3 different classes that use these sets, so sometimes I have to replenish my supply. So what's interesting is, I wish I knew the year. I guess maybe it'll tell us the year when we click on this. It's the student t-test because it's different than the z-score. We're looking at t-scores versus z-scores. And the reason for this is because you don't know your standard deviation of your population. So this gentleman, who, by the way, was not a mathematician, who was not a statistician, he worked for the Guinness Brewery over in Ireland. And he wanted to determine how their means, well, how many samples and how many means of samples he would need to take to represent the population when he didn't know the standard deviation for the population because they hadn't done enough of those, right? So he came up with this. It took him a long time. And I just want to bring up the article just to show you it's for real. I'm not making it up. So here he is. And it's William Gossett. And this was, I think it gives me the year, well, 20th century. He was not a scholar. He brewed beer, specifically Guinness. So he began to think about how I can handle this because I do not have a population standard deviation. So he worked many, many years. He actually took off a year as a sabbatical and did a lot of work. No, I don't want to subscribe to that newsletter. And he came up with this concept of really, I think, describes the difference between a Z distribution and a T distribution. The standard normal is this blue line here. And we've seen that normal distribution many times. But notice a T distribution, N again is going to be my number of samples, right? So if N is close to 30, this bright pink line shows you that it's getting closer to what we think what we know the Z would be. But it's not quite there, but it's darn close. If you have something smaller than 30, the light pink shows the distribution of those samples. So he took many samples. He did some that were going to be a lot less than 30, and he looked at the distribution. He took more that were close to 30, and he looked at the distribution of those means. He did many with more samples, 100 samples. And he found, of course, we are going to be the more samples, the closer we get to the Z distribution. So, because, of course, there's always competition in beer, there's even more now with all the craft breweries, right? Guinness would not allow him to publish his works. They said, no, we have the upper hand because it's going to save us a lot of time because we don't have to take as many samples. We can do less samples based upon what you found out. Well, they didn't want the rest of the brewing companies to know all that. So they came to an agreement, and he published the work, and there's the work, and guess what that work is? Really that table that I just handed you. Or that table comes from this work. That's why he became student. Instead of the Gossett T distribution, it's student T distribution, simply because Guinness would not allow him to use his name when he published his work. So I thought that was a really cool story of how this all came about, and I wanted to take a minute and share it with you. Pretty interesting guy, pretty interesting story. So that is what came up and why you have that T distribution that's sitting there right now. So what do? So first we have to talk about the requirements, just like the other requirements we've talked about with other different uses. The procedure we use has to have one of two things. It has that the population is already normally distributed. If that is true, it doesn't matter how many N you have. If you do not know if the population is normally distributed, then your N sample size has to be greater than 30. There was a question on the last exam similar to that when we talked about the central limit theorem. Okay, so really the same requirement. Notice margin of error. So here's the difference. When I did margin of error in the previous, we did proportions again, not means, proportions, and we knew the standard deviation. We knew that it was normally distributed, and we used the z-score, which we're all very comfortable and used to using. Because I do not know sigma, standard deviation, I have to use now t at alpha divide by 2. Just like I would say z at alpha divide by 2, I'm using now t at alpha divide by 2. Well, I have to add one extra component to it, simply because we saw on that curve from Gossett's work that as n increased, it got closer and closer and closer to the normal curve. So n does affect it. Absolutely. So that's where we come up with degrees of freedom. That's where degrees of freedom comes from. And degrees of freedom is simply n, your sample, minus 1. Okay? And with that comes your new table. So I'm just going to steal this one because the two of you can share for a second. That's your pink table, and it is your t distribution table. Got to know how to read the table. First, I've got to know about my degrees of freedom. So if I said n was 30, if I had n of 30, I'm going to subtract 1, and my degrees of freedom is going to be 29. So along the first column are my degrees of freedom. So I would go down to 29, but then there's all these choices for degrees of 29. I have to decide which column I use. Well, my alpha is going to tell me that. Okay, my alpha is going to tell me that. So if I had a 95%, so we can use this table, if I had a 95% confidence level, right, we know that alpha is what? 5% of 0.05. That would be my alpha for a 95% confidence letter, just like we did in the previous section. Because we have a choice of doing one tail and two tail, and that goes into hypothesis testing, which we'll get to in 8. We have to use this chart, and we have to know if we're talking about one tail or two tails. So that's what all that stuff means across the very top. Okay? We want, for this whole section, we want the alpha 0.05 in two tails. So that's that second row there, or the middle column, where it said area and two tails and it says 0.05. We're going to come down there to where it says degrees of freedom to 29, and it will be 2.045. Does everybody see that? Notice it's still the same column, because if you look right above area and two tails of 0.05, right above that, that whole line there says area and one tail. Well, that means each tail has what? 0.025, which we already know from the previous lecture, right? But make sure you're reading the correct line and you're thinking the correct way when you decide which column to use for your degrees of freedom. Does that make sense? Okay, that's how you read the table. So now that we can find t of alpha divided by 2, this should look pretty familiar to you. We're going to take and multiply by the standard deviation of the sample divided by the square root of n, n being the number of in our sample, okay? For the degrees of freedom, this n remains as was. This n remains as was. So if I had a sample of 30, I'd put 30 in for n. But my degrees of freedom would be 29. Nadira?
Print out the package if there's none, there's no extra in the package.
Sure.
If there's, or would it be?
So which, for the,
This packet.
I gave them out like,
Yeah,
I know, but I don't, I can give you one after class. Okay? Okay. All right. And I'll post this too. Okay, so this is how T is found. T is the, and that should look familiar to you, the x bar minus mu divided by s divided by the square root of n. So degrees of freedom, just so you have that definition, it's for a collection of sample data. And really the way that it comes about is to be n minus 1 is that, let's say that we had 10 scores on a test and the average was 80. 10 scores on a test, the average was 80. If I summed all those up, I'd have to get 800 as a total of scores because I divide by 10 and get 80 back, right? So that last score, the 10th score, I could have all these scores, 9 of them. That 10th score would have to make the difference between this total and 800. So that's why it's a minus 1. I know that's a little technical, but I won't test you on that. But I just wanted you to get an idea that there was some thinking as to why the degrees of freedom is n minus 1. And that's why it works. Here's our notation. I always like to give you that. You also see mu like that for your population mean, x bar your sample mean, again s is your sample standard deviation, n your number of samples, e your margin of error, and your critical t value that separates the area, right tail, will be alpha over 2. Okay? So very similarly that we did last time, we're going to find and calculate the margin of error. When we don't know what sigma is, we're going to use the t. We're going to subtract it from the mean of the sample and add it to the mean of the sample. So here's the procedure. First thing you're always going to do is verify that the requirements are satisfied. What are the requirements? You got 2 that you can, one of 2.
It's either normal distribution or the sample margin of error.
Great. So it's either already a normally distributed population, and you know that, or your n is greater than 30. We're going to use table A3 for our degrees of freedom, n minus 1, to find the critical value for t of alpha divided by t. And remember that chart, you just look to see if it's alpha in 2 tails or alpha divided by 2 in 1 tail. We're going to calculate that margin of error using that formula. We're going to subtract it from the mean and then add it to the mean. Round confidence intervals as such. If you are given the sample statistics, what do I mean by sample statistics? If you're given the mean, you're going to round it to the same decimal point as the mean. If you're given a sample, because we could give you a sample, if you're going to be given a sample, you're going to round it to 1 decimal point beyond. So if my sample were all whole numbers, I would then round it to the 10th place. Okay? If it's a sample, you round 1 decimal place further. If you're given the sample statistics, meaning you're given the sample standard deviation and you're given the sample mean, you're going to keep them rounded to the same point, to the same decimal point. Okay, here we go. Anybody in here a garlic lover? No one's a garlic lover? Oh my gosh, my kids tell me I can't cook without it. Must be part of that Italian part, right? Yeah. So I've heard this before, that a common claim is that garlic lowers your cholesterol levels. So they did a test for the effectiveness of garlic. There were 49 subjects. Right there, 49 subjects. I've met the restrictions. I've met it because my N is 49, right? I don't have to worry about if it's normally distributed. N's 49. Were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. The change in their LDL, that's the bad cholesterol, right? Have a mean of 0.4 and a standard deviation of 21.0. These are not actual raw data, right? They are our sample statistics because it's telling us what the mean is. It's telling us what the standard deviation is. We didn't have to do a calculation to find it. It is my sample statistic. Because it's my sample statistic, this goes to the 10th place. They're enforcing that this goes to the 10th place because they're saying 0.0. That's a significant digit. So I know right now I've got to round to the 10th place. Okay? So I'm going to use the sample statistics of N equaling 49, the sample mean of 0.4, and the sample standard deviation of 21 to construct a 95% confidence interval estimate of the mean net change of LDL cholesterol after the garlic treatment. Then, what does the confidence level suggest about the effectiveness of garlic reducing LDL cholesterol? Okay, so on that test, you're going to be thinking, is this a proportion or is this a mean? It's a what? It's a mean. It's saying mean, right? It's not saying proportion. It's not saying percent. That was the last section. So I know now I have to look at, do I have the population standard deviation? No, that's the population standard deviation is sigma, remember? I'm not given that. I'm given the sample standard deviation. So that's what's going to alert you to say, oops, that means I have to use the t-test. Think of the Brewery of Guinness. That's what they had to do their samples, okay? So I know I'm going to have to use the t to find my margin of error. So let's think about it. My degrees of freedom is going to equal 49 minus 1 to get 48, correct? Okay. My confidence level is 95%. That means alpha is 0.05, and it's going to be 0.05 in 2 tails because I'm going to divide and put half on each side, right? So that's going to be in 2 tails. So I'm going to look at my chart. I'll still hear whatever I'm close to. When I look down my degrees of freedom, I have a little problem here, don't I? Because I'm looking for the degree of freedom of 48. My chart doesn't give it to me. It says 45 or 50. And there's some argument of what we should do. Some say you go to the closest one, and some say to be safer side you go to the next lower. I know. So we're going to go to the closest one. We're going to go to the closest one. So 48 is closer to 50 than 45. So everybody sees that line, right? Okay, then I have to go to my column where alpha is in 2 tails of 0.05. What am I going to get for my t? Critical score. 2.009. 2.009. So t of alpha divided by 2 is 2.009, correct? Everybody okay? So my formula, which you'll have, I think it's under there, under 7. My margin of error is equal to t of alpha divided by 2. Then I'm going to multiply that by the sample standard deviation divided by the square root of n. Isn't that my formula? Where sigma is unknown, and it tells you that on your formula sheet. Okay? So let's fill it in. Error is t of alpha divided by 2 is 2.009. We're going to multiply that by s. S is the sample standard deviation, which it gave me, which is 21. Then I'm going to divide by the square root of n, and n it told me was 49. Somebody will run that through. 6.027. 6.027. So that's my margin of error. My sample mean, x bar, was 0.4, correct? So, to construct my interval, I'm going to take my mean, I'm going to subtract my margin of error, 6.027, sorry. When I do that, what do I get? A negative 5.627. And then I'm going to take my mean of my sample, x bar, and I'm going to add the margin of error, 6.027. And when I do that, I'm going to get 6.427. Okay? Constructing my interval, I'm going to say from negative 5.627 has to be less than mu, meaning the population mean, which has to be less than 6.427. So I am 95% confident that the population mean will fall between negative 5.627 and 6.427. Because we've got all these numbers going, don't lose context of what the problem was. The problem was about the change in LDL when subjects were treated with garlic. Okay? So, we're confident, 95% confident, that the mean of that change is between negative, which means what? Yeah, and between positive number. So what do you think about? What do you think about the results of that? Does garlic lower cholesterol?
Seems like it can.
Maybe. But what's really interesting in this mean is that isn't 0 in there? 0's in that confidence interval, isn't it? So I could have no change. So I don't know that I would go out and publish anything that says that garlic's gonna, right? Yeah.
If 0 is in there because you have negative 5.
Yes, correct. Right. So I don't think garlic has any effect on your cholesterol. That doesn't mean I'll stop eating it. Okay? Does that make more sense after we do a problem? Okay, good. I probably went through it. Example, I did, but I just did it on the other thing. So we already really kind of talked about the properties of the student T distribution because I brought up that article for Gossett, and it should be the Gossett T distribution, right, instead of the student T distribution, but Guinness wouldn't let him publish his work with his name. So we know that there is a difference for when n equals 3 and n equals 12. The higher the number of n goes, the closer that t distribution curve is going to come to the normal distribution of the curve. What's nice is 0 is still 0. The mean of a t-score is still 0, like the mean of the z-score is 0. What changes is the standard deviation. Because as we saw on that drawing, let's get some different colors going here. That could be kind of the difference depending upon the n. It's going to be wider, it's going to be broader, right? Because it's going to be wider and broader, it will be having a standard deviation greater than 1. The more the n, the higher the n, the closer it's going to get to the standard deviation of 1. Okay? We kind of saw that from that article and Gossett's work. And there it is again, a nice picture. You can see the blue being your standard normal distribution. The one in red, can't see here, the one in red has an n of 12. See how the red one is getting closer and closer to the standard? And then the distribution with an n of 3 is this kind of mustard color looking one, and it's further away from the normal standard distribution. That's why we have to meet those requirements. Either the population is normally distributed or n is at least 30. So just like before, we can go backwards. We can find things out the backward way. In other words, if I already have a confidence interval, if they give me the confidence interval, I can use those numbers to find out the mean of the sample. I'm just going to add them up and divide by 2. I can also find my margin of error by taking the difference and dividing by 2, just like we did with the proportion ones. Exactly how we did it with the proportion ones. So now let's look at the formula for finding a sample size for estimating a population mean. Again, there's the notation. Of course, mu is population mean. Sigma is the population standard deviation. X bar is the sample mean. E is our margin of error. And Z, alpha divided by 2, is the z-score separating them out. So there's my, what way of finding the sample size. And again, just like before, we're going to go up to the next larger whole number, because if I went down, I wouldn't have that minimum. Okay? So, as we said before, many times, most times, I wouldn't be needing to find out or estimate the population mean. If I had the population standard deviation, I would already know it. So I have to use my rule of thumb, which estimates the standard deviation of the population. And that's this formula here. I'm going to take the range. Remember what range is? The difference between the highest number and the lowest number. And I'm going to take that range, I'm going to divide by 4, and we're going to use that as our estimate of the standard deviation so that I can pump through this formula to find out a sample size. Okay? And of course, I'm just going to use my formula to find it. Another way they also often do it is using the first couple of samples. They'll use their standard deviation and then use many of them and then use that as the estimate. We will not be doing number 2. We'll be using number 1. We'll be using this range divided by 4 to approximate the standard deviation of the population. Okay. So here's our example. We'll assume we want to estimate the mean IQ scores from the population of statistics students. How many statistics students must be randomly selected for the IQ tests if we want a 95% confidence that the sample is within 3 points of an IQ score? Okay? So now I'm doing the sample. This was nice. It gave you alpha. It gave you alpha divided by 2. Then it gave you z. Notice again, now we're using z. We're not using t. We're using the z table, just like we did before. Z of alpha divided by 2 is 1.96. Our error is 3 points. And we do know the population standard deviation of an IQ test. We have that memorized now. The mean is 100 and standard deviation of 15. So, do you think that statistics students mean is going to be different than population mean? I've got some people going, yeah, I agree. Why? If we're a sample of the population, you guys are a sample of the entire population. Okay? So your IQ scores are going to be what? Higher than the entire population as a sample. Because you are a sample. Okay? All right, so let's figure it out. What kind of a sample would I need to take of just statistics students, not the population, just statistics students? So n is going to be equal to what? I've got this great big thing, I've got a square, right? Whoops, I'm writing n instead of square. And I'm going to take what? Z at what? Alpha divided by 2 on your formula sheet. I'm trying to find it. Okay. So it's the one under Chapter 7, which is sample size determination. N is equal to that, and we're going to take Z of alpha divided by 2 times the standard deviation divided by the error. So for this problem, alpha divided by 2, Z of alpha divided by 2, 95%, confidence level, right? We have 1.96. We're going to multiply 1.96 by the population standard deviation, which we know, we don't have to estimate it, is 15. We're going to divide that by the margin of error, and it tells me my margin of error is 3 points, not 3 percentage points, but 3 points of the IQ score. So I'm going to put 3 here. Then I'm going to take this whole thing and square it. .04. Could I get away with a sample of 96 statistics students? No. I need an N of 97 statistics students. That would be my sample size. Okay. Notice this is a different formula. Don't get confused. Looking at your formula sheet, just want to make sure I point that out. If you look under Chapter 7, Sample Size Determinations, you have the sample size for the proportion when you don't know Q hat and P hat. The middle one there is the proportion when you know P hat and Q hat. And the last one is this one, and notice we're using that one when we're looking at a mean. That's how you're going to tell them apart. Okay? So this section presents methods for estimating population mean, the values of the sample data, and we also know the population of the standard deviation. So that's if I know the population standard deviation. You already know all of those. There's nothing new there. Notice if I know this. If I know sigma, I'm going to use Z. If I don't know sigma, I use T. Okay, that's how you tell them apart. So the confidence interval for estimating that population mean, when you know sigma, they're just that sigma is just the capital sigma as compared to what I usually write with a not capitalized sigma. Same thing. The sample size has to be a simple random sample. The value of the population standard, sigma, is known. And either or both of these conditions are satisfied, that the population is normally distributed, or N is more than 30. So those are my requirements. And just like we did before, we're going to calculate our error. Notice the only thing that's different between the last one is this is Z of alpha divided by 2. When I don't know sigma, it's T of alpha divided by 2. Same exact formula. Okay? And of course, then I'm going to take my mean and plus or minus that standard error. So here we get to an example. So people have died in boat and aircraft accidents because obsolete estimate of the mean weight of men was used. And we saw that. We did the one where the ferry in the Baltimore Harbor sank. So in recent decades, the mean weight of men has increased considerably. So we need to update our estimate of the means so that the boats, aircrafts, elevators, and other devices do not become overloaded. Using the weights of men from a random sample, we obtain these sample statistics for the simple random sample. We used an N of 40, and from that N of 40, we found the mean weight of those men being 172.55 pounds. That's our sample statistics. Research from several other sources suggests that the population weights of man have a standard deviation of sigma is equal to 26 pounds. Right there, you know you're using Z. You're using Z because I have the population standard deviation. That's the difference. That's what you need to look for on your mini test that's coming up, right? So find the best point and estimate of the mean weight of the population of all men. That's going to be the X bar, right? And that was 172.55. I know, I go to the next screen and I don't have my numbers there, so you guys have to help me. So, and I'm going to construct a 95% confidence interval estimate of the mean of all men. How am I going to do that? I'm first going to calculate what? My error, my margin of error. My margin of error, because I know sigma, I'm going to use Z. Z of alpha divided by 2. I'm going to multiply that by what? The standard deviation. And I'm going to divide by the square root of n. That's my formula. When I know sigma. In this example, I have a 95% confidence level. So Z of alpha divided by 2 is equal to what? Anybody remember that chart? 1.96. I'm going to multiply by sigma. Sigma was on the previous page 26 pounds, is that right? Then I'm going to divide by the square root of n. What was n? 40? What do you find that error, margin of error to be? $8.05. We got agreement? 8.057. Okay. Now I am ready to construct that interval. So I'm going to have my mean plus or minus the standard error, correct? So my mean was 172.55 pounds. I'm going to subtract 8.057. Then I'm going to take my mean, 172.55, and I'm going to add my standard error of 8.057 pounds. Somebody's going to help me out. 180, 61, 607. Okay. Okay. And we'll round it in just a second. I want to absolutely round. And 172.55 plus 8.057 is,
Plus.
okay, I was going to say, wait a minute. That was the plus. Okay? 180.607. Okay. So now that we've added and subtracted, let's write our confidence interval. So 164 point, and we're going to round. You tell me what I'm rounding to. What's the rule? What was I given? Was I given this the statistic, or were I given lots of raw data? I was given the statistic, wasn't I? And the statistic came to me to the what? To the hundredths place. So I'm going to round to the hundredths place. So 164.493 is going to be 0.49, which is going to be less than mu, my population mean, which is going to be less than 180.61, again, rounded to the hundredth place, because that's what I got my statistic in, to the hundredth place. So there's my confidence interval. I'm 95% confidence that that mean, population mean, is between those two values. And part C says, what does that result suggest about the mean weight of 166.3 pounds that was used to determine safe passenger capacity in water vessels in 1960?
No longer the case. The mean is higher than that.
Probably.
In between 164
It,
and 80.
right, and they're saying
163.
that was what, 160 what? 166. Why 166 is in here? Yeah, but you know what? It's at the downward side, isn't it? So if I were going to be designing for safety, would I want to use a mean weight that's low, on the low end, or would I overcompensate? I would overcompensate and at least go to the upper end. Definitely. Definitely. I just gave myself spots. Okay, this is this little chart to show what you need to do. I think I've pretty much drilled that home. When I'm doing a confidence interval for mean, I'm going to start by deciding if I know the population standard deviation or not. That's my first step. If I know it, then I'm going to go this way and decide if that's normally distributed or if it's over 30. Then I'm going to use my z-score. This one is when I don't have a normally distributed population and my n is less than 30. This is called a non-parametric, or it's bootstrapping method. We will not be doing that in this class. Okay? You'll be doing that if you take 2. Okay? If you do not know your population standard deviation, of course, you're going to end up using the t-distribution. The t-distribution. If it's normally distributed or if n is greater than 30. Okay? Again, if not, in a situation like that, again, it would be a bootstrapping method that could possibly be used, or a non-parametric. Okay? And I think that's it. Nope. Again, we reiterate the same thing. I want to make sure, boy, I did drive that home, didn't I? Okay. Just so that you know, I really put it in multiple ways there. Okay. Very good.